Well, good day, everybody. And we are in our discussion of gases, and we have started into the concept of gas laws. Now, let us get into the next part. Consider 0.70 moles of carbon dioxide gas, okay, in a rigid 12-liter container at 25 C and the pressure, right? The question is, what would the volume be? So we're going to look at volume if the temperature were decreased. So we need a relationship between temperature and volume. Okay, let's go up to our notes. And eeks, they've disappeared. What are we going to do? Well, I guess we're going to have to start all over. Here's gases, and we talked about the kinetic theory, and we talked about a definition, and we talked about pressure, and we talked about all kinds of conversions, right? 1 atmosphere equals what? 14.7 psi, which is equal to 760 torr, which is equal to 760 millimeters of mercury, which is equal to 101.3 on your kPa dial, right? Good. So that's our pressure. And then we started talking about some gas laws. And that's where we are now. We're talking about gas laws. We started off with one that's called Boyle's, and I don't really care if you know the names. I don't think that's so important. And that is P1 V1 equals P2 V2. And we said, hey, what's held constant here? Well, constant are my moles, which is N. N represents moles, and temperature. Good. And then I think we had what? Avogadro's law, and that is V1 over N1 equals V2 over N2. And we said the N is my moles, right? And V is volume. And that would mean what? Pressure and temperature are constant. And we had Gay-Lussac, and that is what? That is P1 over T1 equals P2 over T2. And what's constant? Moles and volume are constant. And what's very important here is T must be in Kelvin, right? And how do I get Kelvin? Well, Kelvin is equal to Celsius plus 273.15. Remember, Kelvin is absolute zero, so Kelvin can never be negative. Cool. And now we are moving on. What was the next one? We said we are relating volume and temperature, and that is Charles's law. Charles. How about we spell it right? Charles's law, and that is V1 over P. V1 V1 over T1 is equal to V2 over T2. Any volumes, uh, moles and pressure are constant, but what must be true about T? T must be in Kelvin. So as long as my units of volume are the same, milliliters, milliliters, liters, liters, hectoliters, hectoliters, that's fine. But my T must be in Kelvin. All right. So we can work this now. Here we go. Let's go with something a little brighter. We'll go with our yellow. I like yellow. Good. So V1 over T1 equals V2 over T2. How do I know that I'm going to use this? Well, I have a volume in one case, and they want to know a volume in another case. I have a temperature in one case, and I'm given a temperature in another. So that means I have this, I have this, and I have this. I want to solve for that. What's my first volume? This is my situation one, right? So 12.0 liters over what's T1? 25, but that's C. So what do I have to do? 25 plus 273.15, and that'll give me K, is equal to V2 over 0, but that's not really 0 because that's 0 Celsius, meaning that is 273.15 K. Hey, excellent. So I'll get out my calculator. Where's my calculator? Here it is. Okay, got it. 12, yoink, times 273.15, got it, divided by quantity, 25 plus 273.15, that's 298.15, and I get an answer of 10.99. How many sig figs can I get? Well, this is significant to the units here, so that means I'm going to get out of this, I'm going to get 3 sig figs. I get 3 sig figs here. Actually, I can get 4 sig figs because that was 0, wasn't it? I can go to the tenths here. Yoink. And I have 3 sig figs there, so my answer is 3. So this is what? 11.0 liters. Okay, good. You guys try the next one. Bring me back when you're ready. Well, I have volume and I have a temperature. I'm looking for a volume. Up here I have a volume and I have a temperature. So that means I'm going to use Charles's law, right? As expected. And what is V1? 7.5 liters. What is T1? 25 plus 273. So that's what? 298.15, although the 15 is not significant. Kelvin is equal to V2, that's what I'm seeking, plus, ooh, this is a big number, 250 plus 273.15. That's not going to be significant, right? Because I'm only going to be significant to the units here. All right, here we go. 250 plus 273.15, got it, equals 523.15 times 7.5, yeah, divided by 298.15 C, and I get V2 is equal to 13.15, 2 sig figs, 2 sig figs right there, so my answer is 13 liters. There we go. Hey, nothing to it. Next. Okay, so we have a consideration here. I have moles. Okay, I have moles. I have liters, volume. I have temp, and I have pressure. So I have N1, V1, T1, and P1, right? That's what's given. And we want to know what the pressure is if the volume were increased. So I have a V2, and the temp were increased, and I have a T2. And I want to know a P2. Do I have something that relates V1, T1, P1 to V2, P2, T2? And the answer is not yet. And here we go. Are you ready? There is another law, as you might expect. Where is it? Right here. The other law would be called the named after Mr. Combined. Yes, called the combined gas law. Yeah, it's not really a Mr. Combined. Who are you kidding? V1 or P1 V1 over T1 equals P2 V2 over T2, right? And what's constant? Moles are constant. And what do we know? T is going to have to be in Kelvin. Yeah, I can handle that. And the pressures and volume can be anything as long as they are consistent, right? As long as P are in the same unit and V, as long as they're both in the same units, we can use any units we want for pressure and volume. Got it? All right, that's a piece of cake. Ein Stück Torte, yeah? Gut. Here we go. P1, yips, zoink, yellow. P1, V1, sorry, over T1 equals P2 V2 over T2. Oops, I think I'm in the wrong place, aren't I? Sorry, folks. I went too far. That happens on occasion. There we go. Ask my students. They'd say I go too far all the time. P1 V1 T1 equals P2 V2 over T2. Okay. Where's my P1? Here's my P1. So I have 1.43 atmospheres, and we gotta watch our units. Where's my V1? V1. Do anyone say V1? I better go higher. There we go. V1. 12.0 liters. T1, 25 plus 273. So that's 298.15. That's not significant. K is equal to what? P2. That's what I'm seeking. Times what's V2? V2 is 18.0 liters. And T2 is 125 Celsius plus 273.15 to give me K. Okay, so here we go. Are you ready? P2 is going to be equal 1.43 times 12, good, times quantity, 125 plus 273.15 quantity, good, divided by 298.15 divided by 18, and I get a P equal to 1.2. How many sig figs? 3 here, 3 there, 3 there, 3 there, 3 there. It looks like 1.27 atmospheres. Okay, let's check my numbers just in case. Let's try this again. I take 1.43 times 12 divided by 298.15 divided by 18 times quantity 125 plus 273.15, and I get 1.27. Wee! Winner, winner, chicken dinner. Excellent. I hope you all did the same thing. Or will you do the same thing here? Okay, you guys try this one and bring me back when you're ready. Well, I'm going to analyze this. Maybe this is wrong. Maybe I'm not supposed to use this. Anybody want to make a bet? Good. I have N1 here. There's N1. And I have V1. And I have a T1. And I have a P1, right? And what do I have here? I have a V2. How do I know that's V2? Because it says liters. And I have a T2. Ooh, look at that. And I have what? I want a P2. All right, so I'm going to use the combined gas law. P1 V1 over T1 equals P2 V2 over T2, right? What's my P1? 1410 millimeters of mercury. I would like to write my units so I don't make a mistake there. 7.5 liters over, what's my temperature? 25 plus 273.15. Only going to be significant, excuse me. Only going to be significant to the units here. Oh. And that's going to equal P2 times V2. What's V2? 25.0 liters plus 200. And what have they done here? Hey, it's already in Kelvin. Woohoo! I don't have to do any conversions. Good. Now you guys know how to do this, right? How do I solve for P2? Well, I'm going to multiply both sides by 200, and I'm going to divide both sides by the 25, so I get P2 alone. If, in case you've forgotten how to do this, P2 is going to be equal to 200 Kelvin times 1410 millimeters of mercury times 7.5 liters divided by what? 298.15 Kelvin divided by 25.0 liters, right? And we can check our units to make sure this happens, right? My K's cancel, my liters cancel. What am I left with? Millimeters of mercury. Is that a form of pressure? Absolutely. And let's run the numbers. 200 times 14 point, oops, I got to start all over. 1410 times 200, good, times 7.5, yeah, I got that, divided by 298.15, got that, divided by 25, and it looks to me like I get 280, how many sig figs? 2 here, 283, which would be equal to 280 millimeters of mercury. Let's check that again. Make sure I didn't make any mistakes, okay? 1410 times 7.5 divided by 298.15 times 200 divided by 25, and I get 283. Good. So 280 millimeters of mercury. Yahoo! All right, these are not hard. We just have to maybe memorize a few of these. But hey, let's go back and look at this just for a second. Right? Is there any way, any hints in memorizing these? Well, notice this. What is always, if I have something in the denominator, what is always in the denominator? Well, it's either going to be moles or temperature that's in the denominator. What is never in the denominator? Pressure and volume are never in the denominator. So that might be a way to help you remember that temperature is always in the denominator, moles are always in the denominator, whereas pressure and volume are always in the numerator. Okay, good. Now there's one other law that we want to learn, and it's probably the most important, and it is what we call the ideal gas law. Okay, and it is, like I say, probably the most important. You'll use this for a long time, and it is PV equals nRT. Now notice it's not P1V1. What this allows us to do is that any given situation, if I have one situation, so if I have time one, not time one, I have experiment one, we'll say, if I have any three of these, R is a constant. If I have temperature, moles, and volume, I can calculate pressure. Or if I have pressure, volume, and moles, I can calculate temperature. Or if I have pressure, moles, and temperature, I can calculate volume. And so this equation allows me to figure out, to always figure out pressure, volume, temperature, and moles if I'm given three of the four. Got it? Now, this is R, and R is 0.08206. Now, there are other values of that, but I like 0.08206. And here's what's important: are the units. It is in liter atmospheres per mole Kelvin. Got it? So R equals 0.08206 liter atmospheres per mole Kelvin. But what does that mean? That means my pressure must be in atmospheres. My volume must be in what? Liters. And my temperature must be in what? Kelvin. And my N must be in moles. Good. So this is a little more restrictive. I always have to have atmospheres, liters, moles, and Kelvin, and I have to use R, but like I say, if I have three of these, I can calculate the fourth. Are you ready to do a problem related to that? Here we go. Consider 25 grams of oxygen gas. Okay, 25 grams of oxygen gas. So what? I'm given a situation where I have grams, right? I have at 10 psi, so that's probably going to be P1, or a pressure. I have 725 millimeter container, that's a volume, and it wants to know a temp. So I have grams, pressure, volume, and we want to know temp. Okay, well, how can I do this? I know I have PV equals nRT, but and I have P and I have V. I want to get T. I know what R is, but how do I get N? What is N? Oh, N is moles. Yeah, and moles are equal to what? Grams divided by molar mass. Oh, okay, so I can work this. I have 25 grams of oxygen. Okay, so let's get moles of oxygen. So that's 25 grams times 1 mole of O2 per 2 times 16.00 grams, right? Okay, good. So let's get that. 25 divided by 32, and I have 0.781. That's not significant because, oops, that's 25.0, so that is significant. 0.7812, the 2 is not significant. We always carry one additional non-significant figure. That's moles of O2. I have PSI, so my pressure, though, I need to have pressure in ATM. So I have 10.0 PSI times what? Well, 1 ATM per 14.7 PSI. Okay, so let's take 10 and divide it by 14.7, and I get 0.6802 atmospheres. Okay, good. I need volume in liters. And what's my volume? It is 725 milliliters, but there are what? 1 liter in 1,000 milliliters. So that's equal to 0.725 liters. Okay, I have everything I need. P, what's P? 0.6802 atmospheres. Good. V, what's V? V is 0.725 liters. N. N is equal to 0.7812 moles. R. We're going to have to go on to the next side. 0.08206 liter atmospheres per mole Kelvin. Yahoo. And finally, T, which will be in Kelvin. All right? Good. Let's run the numbers. Okay, so that means I'm going to take 0.6802 divided by, oops, not divided. Oh, I messed up already. Yoink. 0.06802 times 0.725 divided by 0.7812 divided by 0.08206 equals, wow, I must have made a mistake. We better try that again. I got a weirdo number. I got 0.769 Kelvin. Do you think that's right? I don't. Let's try it again. I must have made a mistake. 0.6802 times 0.725 divided by 0.7812 divided by 0.08206. There we go. And I was off by a factor of 10, 7.69. How many sig figs? 3. 7.69 Kelvin. Ooh, that's pretty cold. In fact, I don't know if that's really possible. Let's run those numbers again. Let's make sure I didn't make a mistake. Okay. I take 25 grams divided by 32. Yeah, and I get that number. Good. So that's my moles, right? That 10 divided by 14.7. Yeah, 10 divided by 14.7. That's right. So this is right, and that's right, and that is, I'm certain, is right. Let's run the numbers again. PV equals nRT. P, yes. V, yes. N, yes. R, T. 0.6802 times 0.725 divided by 0.7812 divided by 0.08206, and I get 7.692. That's correct. Woo! That's cold stuff. Yep, come on. Why are we not working here? I guess my hand's too cold. All right. You guys give this one a shot. Bring me back when you're ready. And I'll give you a hint here, right? Fluorine, in case you don't have your periodic table handy, fluorine has a molar mass of 18.99. So this is 18.99. That's for 1F. Got it? Okay, bring me back when you're ready. Okay, I have 250 grams. I have a temperature. I have a volume, and I want to get pressure. So PV equals nRT. What's my P? We're trying to find that. What's my V? Volume is 1.75 liters. Okay, that's good. What's my N? I have to get my N first. Okay, so let's go down here and let's go over here and calculate N. N is equal to what? 250 grams times 1 mole of F2, because it's F2, it's diatomic, over 2 times 18.99 grams, right? Okay, so what do I get out of that? 250 divided by 2 divided by 18.99, and I get 6.58. How many sig figs? 4 sig figs. 2, and I want to carry my extra 4 moles of F2. All right, here, let's move this down here. P times 1.75 liters is equal to N, 6.5824. R, that's moles. R is 0.08206 liter atmospheres per mole Kelvin. And T, what's my T? T is 0, but this needs to be what? This needs to be Kelvin, so 0 plus 273 is 273.15 Kelvin. That's not significant. Oh, well, excuse me, the 5's not significant. Good. Let's run the numbers. 6.5824 times 0.08206 times 273.15 divided by 1.75, and I get P is equal to 84 point, how many sig figs? 3, 3. It looks like 3 driven by right here. 84.3 atmospheres. Wow, that's a lot of pressure. Run the numbers again just to make sure we didn't make a mistake. 6.5824 times 0.08206 times 273.15 divided by 1.75. 80. Okay, that's good. That's the answer. One more, and then we'll call it quits. Carbon monoxide gas at 725 torr and 37 Celsius in a 500 milliliter container. How many grams carbon dioxide do I have? All right, you guys give this a shot. Bring me back when you're ready. Well, this is going to be a PV equals nRT. So PV equals nRT. Now we can always solve for N, right? N is equal to what? PV over RT. Good, because we want to get moles here. We want to get moles of CO. And what's my pressure? Well, pressure is 725 torr, but I can't leave it in torr, right? I've got to have it in what? Well, I have to convert that to 1 atmosphere per 760 torr, right? So now I have that in atmospheres, and I have 500 liters, milliliters, so I have to change that to liters. So how do I make this into liters? 500 milliliters times what? 1 liter per 100 milliliters, so that's equal to 0.500 liters, so 0.500 liters, divided by PV over R, that's easy, 0.08206 liter atmospheres per mole Kelvin. Good, 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 good. And then what's T? T is, where's T? T, 37 Celsius, 37 Celsius plus 273.15 Kelvin. Okay, so I'm significant to the unit, so that's not significant. Let's run the numbers. What are my moles? Okay, 725, got it. Divided by 760, got it. Times 0.5, got it. Divided by 0.08206, got it. Divided by the quantity, 37 plus 273.15, got it. And my answer is 1.874 times 10 to the minus 12 moles of CO. Okay, let's run the numbers just to make sure we didn't make a mistake. 725 divided by 760, yeah. Times 0.5, yeah. Divided by 0.08206, yeah. Divided by, what is that? That's 310. 310, yeah. 310.15, yeah. And I get 0.01874. Okay, good. Moles, but that's not what I want. I want grams. So how do I convert grams to moles? So I have 1.874. How many sig figs? That's not sig. Times 10 to the minus 2 moles of CO times what? Well, I have 12.01 plus 16.00 grams of CO per 1 mole of CO, right? Hey, that's my molar mass of carbon. That's the molar mass of oxygen. Add them together, right? So that is what? Looks to me like that's 18 or 28.01 times quantity 12.01 plus 16. Yoink, that is 28.01. What do I get for my answer? 0.5249. When I round it to my 3 sig figs, I get 0.525 grams of carbon monoxide. Yahoo! There we go. That is the answer. I hope you did well. That will be it for today. Oh, a long day. See ya. Bye-bye.